It's time to start. Can they hear me on the? I couldn't wake up. I didn't have enough tea or something. Arkadaşlar. So today we have our third package of training, and it's going to be on BioExcel building blocks. And I must admit, this is the one I know nothing about, so I'm very excited to learn about it. So as a hospital, he's from IRB Barcelona. IRB stands for Institute for Research in Biomedicine. But he's a computer scientist by training, original training. However, he has been interested, PhD on molecular flexibility, which I understand. So the floor is yours. Thanks for
Perfect. Thanks for the kind introduction. Good morning, everybody. So as you can see in the slide, this lecture is about one particular library that we are developing in BioExcel. I will explain a bit of the library, about BioExcel, a bit of everything during the lecture, don't worry. But the idea is to build interoperable and reproducible biomolecular simulations using this library. So I have a couple of notes for you before starting. I've pasted a couple of lines in the Slack channel, which I think can be helpful for you. One of the links go directly to the GitHub where we have all the materials. You can find the PDF of the 3 different presentations here. One is for the lecture now. Another one is for the tutorial after the lecture. And another one is an extra one, like homework for you if you are interested in knowing more about this. This afternoon, we are going to work with Truba, and also the extra slides that you can find here are also everything that you can do directly using your user account in Truba in a command line way, and also using the Open On Demand platform. We'll have time for that. The second link goes to this shared document that we opened just for you to paste any kind of question, suggestion, comment that you can think about during the lecture, during the tutorial. After today, you can still open the document. It's going to be a live document for you. This is very good for us also as a feedback, because if you think about the module after the lecture, after I introduce you the library and everything, if you think about the new module that is not introduced, a tool that is not wrapped by the tool, or a workflow that is not there, just please write your comments here in the document. And this is something that we are going to use in BioExcel for the development process after today. So I hope that all of you have access to this document. I hope that all of you have edition privileges for the document. And with this and the PDF, you can download the PDF. You can also then use all the links that I put in the presentation, if in case you want to open a link and see all the information related to this. I see people connecting already in the document, so I think that we are good to go. So back to the presentation. So you're going to have me the whole morning. Sorry about this. We have 1 hour of lecture and then 1.5 hours of hands-on session after a coffee break. Both of them are prepared to be very interactive. So what I will try to do is to enjoy all of us together, especially during the hands-on session, using the Open On Demand platform with the Jupyter Notebook, that we can work all of us at the same time in real time. Let's see what happens. And so yes, first session, a lecture, a bit of introduction about the library, also about BioExcel, about why we started developing this library, and all the different results, with a bit of examples of what we've done with the library and the workflows generated using it. Second session, we will work with one particular workflow, which is the GROMACS setup process with a protein and a ligand complex. I know that some of you already have experience with that. Some of you maybe not, but I will try to show you that it's not just the process, but it's all the different tasks related in the process, all the different intermediate results that you can take a look, all the different parts of the workflow that you can go one by one using the Jupyter Notebook, all the cells in a very interactive way. And I hope that you also enjoy the experience. If we have time, we will have a quick view on different workflows, apart from this one, from the collection of workflows that we have available in the website of the library. Okay. Starting from the beginning, I know that you all know Alexander because he's our rock star today in this workshop. Probably you don't know me. I'm a research software associate in Barcelona, working in the group that is led by Professor Modesto Orozco. You all know Barcelona, I guess, so you are all invited if you come to Barcelona to visit maybe the stadium or the Sagrada Familia or whatever. You are invited to the Institute for Research in Biomedicine. You just ask for us and we are going to be there. The group, of course, is focused on theoretical study of biological systems, but we have a particular focus. Oh, Janice is going to help us. He's now connected. He's a full stack developer, one of the main developers behind the BioBB library, and he's connected to the Zoom account, the Zoom Meet. So if you have questions, you can also ask questions in the Zoom. If you ask questions in the Slack channel or in the Google Doc, he's monitoring that so he can answer the questions in real time. Yeah, so we are focused on theoretical study of biological systems, but in particular, we are focused on structures. So we work a lot with different kinds of structures, small molecules, DNA, RNA, proteins, complexes, everything. But what we are interested most is in the dynamics and flexibility of these structures. And that's why we are talking a lot about MD simulations, but we are not just using MD, we are using QM, we are using MD, we are using coarse grain simulation, and also mesoscopy. So we are going from different resolutions and different time scales, but all with the main objectives of extracting this information, this flexibility and dynamics information from structures, macromolecular structures. Apart from that, there's another point that I personally am very interested in, is that we don't want to do that and just publish the paper and that's all. We want to store this information that we extract from these simulations, store this information in databases, and then open this information to the whole community. And there's a particular project that we are now working on that is called Molecular Dynamics Data Bank. This is the first molecular dynamics database in Europe, generic database, federated infrastructure with many different nodes that you can take a look if you are interested. But we have been producing many different databases in the group with the idea of sharing this information, storing and sharing the information that we are generating with the simulations. A bit about BioExcel. I'm sure that all of you know that BioExcel is organizing this event together with EuroCC. You know that these are the partners on the BioExcel project. BioExcel is the Center of Excellence for Computational and Biomolecular Research, but was a project that was funded by the European Commission. We started 10 years ago already. So it's our 10th anniversary this year. And it's now a central hub for biomolecular modeling simulations. And the area of expertise that we have is exactly the same that I was telling you before, the same that we are working in our group, from small molecules to mesoscopic systems. And the partners, that's what I wanted to tell you, is, as you can see here, KTH, GROMACS people, MPG, PMX people, Utrecht, Haddock, and BSC, Barcelona Supercomputing Center, and IRB, which are the main developers of the BioExcel building blocks that I'm going to present today. Apart from that, we have 3 more partners that are helping us. CSC in Finland, Nostrum Biodiscovery is a small pharmaceutical company in Barcelona, and Norman Consulting. We started the project 10 years ago with a clear objective that was enabling better science. And we wanted to do that by improving the performance and functionality of the key applications. Again, key applications, that means GROMACS, PMX, Haddock, and now also BioExcel building blocks. That means maintaining, developing, extending all of these codes that I'm sure that you know that this is not a straightforward thing to do. We need time, we need people, we need resources for this. It's not easy, especially with this popular tools like Haddock and Gromax. We want to provide support to non-expert and advanced users. We have many training events. We have like this one, for example, but we have webinars, regular webinars. You can take a look at the website, BioExcel. You have a link here in the PDF. It's just clicking the PDF, the link, and you have access to this website. Webinars, workshops, conferences. We are doing many workshops like this. So we are trying to provide support. There's also the ask.bioexcel forum for discussion, for questions about all of these tools, and also about the workflows I'm sure that you can find in the BioExcel website. And the last objective, which to me it was the most important one at the beginning of the project, and also now, is developing user-friendly computational workflows. And that's all about the lecture here today. How we want to develop this user-friendly computational workflows, that's something that we started thinking about. We did some kind of brainstorming at the beginning of BioExcel. And we started with the concept of the workflow. I'm sure that you all know that. Very easy. If you think about the computational workflow, we have different processes, one after the other. Can be as easy as just one task, one command line tool, one of these processes, or maybe more than one task, as you can see in these cases, or maybe as complicated as a soup workflow like this one here, with many different tasks, etc., for just one process. The objective, of course, is to take something as an input and create a kind of a result as an output after all these processes. We have one classical example in our field, right? There is the virtual screening workflow. We take all the compounds, a library of compounds. We take the target receptors on the other hand. We put all of them together. We prepare the small molecules. We prepare the protein targets. We try to dock them. Then we score them using scoring functions, whatever. We filter and we get the final set of the poses that we need, that we think are the most important ones, the candidates, let's say. I'm sure that you all know about this workflow. And if you think something sequential, it can be complicated, but it's kind of easy to understand. This is a real workflow. This is a workflow that is behind one of the web servers that I was telling you before in the first slide, that we try to generate the workflow, we try to generate the data, and then we open the data to everybody. So you can also click the link here if you are interested in this. It's a database of bioactive conformers. So the result of all of this workflow was a set of conformers, bioactive conformers, starting from just the smiles. So we generated the structure at the beginning using OpenBubble. We parameterized the structure. We set up the system for molecular dynamic simulation. We were not using classical MD simulation here. We were using Hamiltonian replicate change. The idea here was to push a bit the dihedrals of the small molecule to obtain different bioactive conformers. At the end of this, we clusterize everything, the trajectory with lower temperature for the ones familiar with the replicate change, enhanced sampling technique. And we finally took the centroids of this clustering and ran quantum mechanics on that to optimize the structure. And the result was just this. But this is just an example for you of this is a real workflow, or at least to me, this is a real workflow that we can use every day. Many different tools, many different tasks, some of them easier, some of them a little bit more complicated with HPLC, let's say, methods like this one, the Hamiltonian replicate change. So thinking about the previous slide and thinking about the work that you are doing in your everyday work at your job. So I'm sure that you can think about all these different parts of your work. So I'm sure that you are familiar with the conversion between different formats of molecular file, modeling the structure, of course, MD simulations, QM maybe a hybrid QM-MM system. And then, of course, you are analyzing these trajectories, running docking as we had today, yesterday, free energy that you're going to see in the lecture after this one with Sudarshan, parameterization of ligand, that, all of these, I'm sure that you're familiar with all of that. If you're lucky, you maybe have access to this kind of platforms, fantastic packages, all of them requiring money. If you have something like this, graphical interfaces, everything integrated, that is fantastic, but it's not typically the case of research groups like ours. So what we do is to try to run all these tasks using all these plethora of tools that we have, some of them open source, some of them requiring a license, but it's for academia, it's okay, like the one for Amber, Modeler, for example. But yes, this is just a representation. I'm sure that if we have kind of a quiz here, we can end up with 5 different slides like this with different tools. I know that this is just something to represent the amount of tools that we are using every day, right? MD, something to visualize, chemoinformatics, analysis of trajectories, docking, modeling, something about machine learning, QM, a bit of everything, right? What we do with all of this, or what we typically do in the past, but I'm sure that this is still the case now for most of the research institutes. Even if you think about this is a shell script, but you can think that now everybody is programming in Python. But more or less the idea is the same. We have a shell script with all the different steps from the first one to the last one. Think about that. This is just, I'm sure that you cannot see that, but this is just a setup of a molecular dynamic simulation of a structure, so building the box and adding the water molecules and everything. This is something that, if you think about that, has many, many problems associated. So in terms of usability, and this is something that now is changing, because I know that you can use ChatGPT, for example, and you can ask ChatGPT to add all types of comments to your code. That's fantastic. But imagine if you take something like this in 4 years, even yourself, even if you wrote this code by yourself, try to understand what the hell was that line that I wrote here. Even with comments, it's a bit complicated, but the usability here is it can be improved, let's say, right? Interoperability between the different tools, that's something that I'm going to show you in different slides, but it's not easy to find a tool that is producing a format that is compatible with a different tool. You need to go for the tool that is compatible with this particular format. You need to find it before. So interoperability in our tools, in our field, is something that we need also to improve a little bit. Portability, very important, at least to me. If you want to share this workflow with a colleague, if you want to move from one computer to another, you need to be sure that the version of the tool that you're working on with this particular script in your computer is exactly the same that it's going to be installed in the other computer. And if you think about workflows like the one that I showed you before, it's not just one single tool, it's like 6, 7 different tools that they need to have exactly the same version if you want the same kind of results, or just the workflow to run, because most of the times with a different version, something is broken and the workflow is not running anymore. And this is completely linked to reproducibility. So that's something that journals are starting to ask for now. You can publish something, but they are now starting to ask for, okay, so this is the result of your workflow, pipeline, whatever. But if I want to reproduce that, what should I do? And this is something that you should start thinking about, because it's not something that you can just tell them, this is the script that I used in this particular supercomputer or machine that you cannot access, and this kind of thing. So that you need to start thinking about how to reproduce, how to make your workflows reproducible. You'll see that this talk is more about what you need to think than not about the library by itself. So I will be happy if you just keep in your mind all these concepts about reproducibility, about FAIR, about all the different software tools that I'm going to show you that we are using, but I'm sure that they can be helpful for you. Last point, and also very important, scalability. If you think about your workflow that is running in a Jupyter notebook in your machine, that's fantastic. But if it's a molecular dynamic simulation or something that requires computational resources, you need to think about how to scale this. And this, again, is not something that you can just take the shell script and use it in a supercomputer without tuning everything. Okay. Those are the main points that we put together in the brainstorming at the beginning of BioExcel. We decided to look what we had in Europe. And at that moment, and still now, there's a huge infrastructure, life science infrastructure. I don't know if you're aware of this, that is called Elixir. it's more than, I think that it's 23 different countries involved in this project now, more than 250 research institutions involved in Elixir, so huge project. One of the main objectives of the project is to push for best practices in research software and in workflow development. That means applying these FAIR principles that I'm sure you all know, that it's applied to data. At the beginning were applied to data, now also to software development and workflow development. So we decided to align with them, and that was the beginning of the idea of the concept of the BioExcel Building Blocks library. Right. So what is the library? What is this BioExcel Building Blocks library? It's something that the concept is very, very, very easy. It's just a Python wrapper on top of different tools. If you think about the slide before with all the different tools here, with all the different logos, you can think about one particular task using one of these tools, and you put the task here as the execution, right? Then what we do, what the library is doing, is just to add this Python compatibility layer. We are making these tools interoperable between them. So we are accepting a unified syntax as input files and configurations, which is the parameters. We call it properties, but are the parameters of the particular command line tool. And then we adapt these input files and properties to the local input parameters, to the ones that the tool understands. And then we do exactly the same. We take the output of this tool and we basically adapt them to a uniform syntax. Our uniform syntax is the syntax that the library is using. It's so easy, but it's so powerful that we can have a collection of different building blocks, wrapping different tools and tasks using different methods. And then we can put them together one after the other. The same that I was telling you at the beginning, this is a workflow. You just put together different kind of tools and executions and methods, and you build your own workflow. And then on top of that, we are deploying the workflow and we are running the workflow. And to do that, we are using different, what we call workflow managers. Jupyter Notebook is a workflow manager, for example. It's something that lets you build and deploy and run a workflow, but there are many different workflow managers, some of them graphical user interfaces, some of them complicated HPC-focused workflow managers. I'm going to talk a bit about this also in the presentation. This extra layer that you see here in blue is what we call workflow manager adaptation layer, is the layer that we add to be compatible with different workflow managers. So in Jupyter Notebook, we don't need anything like that, but for more complex workflow managers, such as the HPC ones, we need this kind of adaptation layer to make everything compatible. Okay. This is an important slide, but I'm not going to go deeper in all these different logos that you can see here. I will talk about the different technologies that you can see represented here during the presentation. I'm sure that they can be really helpful for you in your work. I'm sure that you all know about GitHub. I'm sure that you all know about Read the Docs, maybe. Read the Docs for documentation is what we are using for the documentation of the library. And we're going to see examples of that. We have packaging, Conda packages, containers like Docker and Singularity, and the different workflow managers. All of this is what Elixir recommends as a fair software development or workflow development. But from all of these, some of them are for findability. So it should be an easy way to find your software and your workflows. They should be uploaded into repositories like Elixir BioTools is one in BioExcel, but it's also Workflow Hub that lets you upload workflows, and then you can then download with all the instructions on how to reproduce these workflows. There's many things that you can do. Of course, GitHub is giving you visibility if everything is there for the user to take a look and download and install. Many different things, but again, I'm not going into details on all of this. Just I need to explain one of these because we are relying a lot on Conda packages in the library. So how many of you know about Conda packages? Can you raise your hand? Okay, fantastic. So it's going to be new for most of you. which is amazing because it's one of the objectives, as I was telling you before, is just to show you all of these technologies that I'm sure they can be helpful for you. So the Conda packaging is just a software tool that lets you do something like this that is really, really important. Imagine that you have a workflow in this computer here, right? And the workflow is using all of these tools that you can see, all of these programs. With these particular versions, you run the workflow and you obtain the results, right? You can build a Conda environment, which is a closed environment with all of these tools integrated in this environment, installed in this environment, and then you run the workflow and you obtain the results. But you run the workflow in this closed environment, right? Which is inside this computer, but it's a closed environment. Then you want to share this. Remember the portability? I want to share this workflow with my colleague. Then you move to person number 2 computer, and in this computer, what you have is all of these tools that you can see here. One of these is not installed from the previous ones. The others have different versions, as I was telling you before. You try to run the workflow, and the workflow is not running because it is missing some dependencies, and some of the dependencies have different versions, right? But what you can do using Conda is to build the same environment, the same that we have here, just reproduce the environment in a different computer, and then run the workflow using this environment, which will have all the dependencies that the workflow needs. And you will be able to run the workflow and obtain the results. And this is what we call reproducibility. And this is one of the main objectives of the building blocks library. And we're going to see examples on that today in the hands-on session and also in the lecture. Okay. Remember that if you have questions, you have the live document and also the Slack channel. You can ask there, or you can put any comments that you want. So with this in mind, with the Conda packaging in mind, with the interoperability of the different tools in mind, we started developing that. And it's always nice to me to show this slide because I started showing this slide a while ago with just 3 different modules. We call it modules because we gather together, for example, all the building blocks, which are all the different wrappers that we have, for example, for GROMACS or AMBER in MD, but also analysis. That means that we are mixing different kind of tools to analyze trajectories, and we put them all together in this different module. All of these modules, as you will see in the next slide, are they have their own GitHub repository, and that means that they will also have a Conda package associated, but that's for the next slide. So the information here is 20 different modules we are still developing. You cannot see that many others to come. For example, I think Haddock is not here, but we have a first version of Haddock 3, and we are working with many others. Yeah, MD, QM, modeling, analysis of structures, flexibility in terms of coarse grain simulations, interaction potentials, that is it's a nice one. Protein docking, protein ligand docking, vitro skinning, these kind of things. This is what I was telling you before. All of this information can be found in the website of the library. You have the link here in this slide too in the PDF. Remember, you can click and you can obtain this information directly. So for each of the modules, this is an example, BioEB analysis, we have the building blocks here. So for example, we have one building block to clusterize the trajectory using GROMACS. This is called GMX cluster. We have different analysis building blocks using, for example, CPP trash from AMBER tools. And we can add new ones if you think something is missing, that I'm sure, because we don't have MD analysis, for example, here. We don't have MD trash, but we can put these tools here. So RMS, for example, from a trajectory, radius of gyration, those are different building blocks. All of this in one particular GitHub repository with the read the docs documentation associated to this particular collection of building blocks. And we are going to see examples on that. All of this packaged in Conda and also in Docker and Singularity containers, which is a different way to package also all the dependencies in one single, in this case, instead of an environment, a container, right? That's for another day. So basically what that means, having one Conda package for us, what means is that if you run in your computer, having Conda installed, which is a very easy thing to do, and there's a tutorial also in the BioExcel Building Blocks website, you can type conda install BioEV analysis, and this will automatically install all the dependencies that all these building blocks need. In particular, in this case, Amber tools and GROMACS will be automatically installed in this environment, this closed environment, so that then you can use all the building blocks that are integrated in this module. This is the analysis one, but there's the example of the virtual screening one, for example, that is going to install automatically for you Autodoc Bina and FPocket to find the pockets in the FPocket to find the pockets in the trajectory, Autodoc Bina to try to dock a small molecule in the cavity, for example. All of these will be installed with just one command line, which is conda install, and the package and the module of the library. More information about the library that we are going to use in the hands-on session this afternoon is the syntax. So the main point about the library is to make the tools interoperable, but we also like to have a uniform syntax so that you can use all the building blocks for all the different tools that we have in the library using exactly the same kind of programming language. So for example, this is Python, of course, but we have the import of the building block always. First one, importing the building block. In this case, we are importing the edit.conf from GROMACS, which is the one that are people familiar with GROMACS. You know, edit.conf is the tool that it's integrated in GROMACS to generate the box surrounding the molecule. So we import this building block that, of course, is wrapping the tool in GROMACS, right? We define inputs, outputs, and properties. So we define in the file system, this is just a string in Python. We define this is the input. We define the output and the properties. And the properties in this case is, okay, the type of the box, I want it to be cubic, and the distance to the molecule 1 nanometer, because GROMACS is working in nanometers, you know. And then launch the building block with the inputs, the outputs, and the properties. And this is going to create this particular box without the water, but the box surrounding the molecule. So this is the syntax. And this, for example, is using the syntax to model a mutation, a particular mutation on a residue of the protein. We import the mutate building block. We define inputs, outputs, and properties. In this case, the property is going to be, I want to mutate the valine to an alanine, and then launch the building block with the inputs, outputs, and properties. This is the mutation, but it's exactly the same. We are wrapping a different tool, but the syntax is exactly the same. And another example, we want to find a pocket in a trajectory. So we import FPocket, we define inputs, outputs, and properties, and we run the building block. So the idea is a uniform syntax for all the different building blocks that we have in the library. With this, we can do something like that. Yeah, it's too small for you, I know, but the idea is very simple. This is a ligand parameterization workflow, automatic parameterization workflow using AC pipe. This is not fantastic, I know. People familiar with this, you know, there's no protonation state here. We are not examining where the hydrogen atoms are placed by open bubble in this case. But in any case, it is something that you can use in a high throughput workflow. You download the small molecule, you add hydrogen atoms, you minimize a bit that, because then we are going to use this in the MD simulations, and then we parameterize it using AC pipe. All of this, 4 different building blocks, one after the other. And this is just a workflow that you can easily generate in a Jupyter notebook, for example. And then you can export this workflow. You can port this workflow to a different computer. To do that, the only thing that you need using Conda is a YAML file like this. And the YAML file is just saying, okay, this is the name of my workflow, channels of Conda, this is not important. And the dependencies is I need to work with BioEV input, output, and I need to work with the BioEV chemistry modules. Remember that this is going to install automatically open bubble, AC pipe, and everything that is needed, all the dependencies that the workflow needs. And this YAML file is used by Conda to generate this closed environment. And then you can run the workflow in this closed environment. And you have all the dependencies that you need to reproduce your workflow in a different computer. Yeah. If you think about these properties and inputs and outputs that you need to define, that's the only thing that it can be a bit complicated, or you may think about what are the kind of inputs that I need to define or the properties that are compatible with this particular building block. That's why we have the documentation that I was telling you. This is read the docs. It's a kind of a standard way to document libraries like this. And for each of the building blocks that we have something like this with information about what the building block is doing, information about the inputs and outputs, which ones are mandatory, which ones are optional. And then we have the list of properties that are compatible with these building blocks that, of course, are related to the tool that we are wrapping, right? In this case, you have here AC pipe as an example. You also have examples on each of these read the doc documentation like this one that to me is fantastic because when I start to work with the Jupyter Notebook, what I do still today is go to the read the docs documentation. I take this, I copy that, paste it in the Jupyter Notebook and start changing, for example, the properties, defining the inputs and outputs that I have. But I have all the import, I have all the launch, I have everything that I need. I just need to change the different parameters that I want to add. And this is in the read the docs for all the different building blocks that we have. So we started to generate these different modules. We started with GROMACS because this is BioExcel and we wanted to try. We started with something like this, GROMACS protein MD setup. Let's try to do a setup of the whole process of just preparing a structure to be used to run a molecular dynamics simulation, adding the box, adding the water molecules, adding the ionic concentration, minimizing the energy, equilibrating the system, everything to have this system prepared for the MD simulation. That was working really well, and we started developing more. So now we have different setup processes for protein, for DNA, with AMBER, with GROMACS, this ligand parameterization that I showed you before, but we have docking, we have free energy, something very specific such as DNA helical parameters, many different workflows that you can visit in this link here. If you want to know more about the library, I'm going to stop about publicizing the library here. So you have the paper that we published a while ago with the concept of the library, and this that was published 1 year ago about not just the library, but the reproducibility of the workflows and how to make your workflows reproducibility using the library or using, if you want, all these software methods that I try to introduce to you. Many different links, webinars, websites, publications just for homework if you are interested, but everything is in the PDF, so you have access to all of this. So questions on this part? I have a second part, but questions on this, on the library?
Not largely, but I mean documents. Different packages require compatible with the two versions. But one package works with level 8, the other one 12.1.
Yeah.
So can I create different environments at the same time with the versions because it's not so page.
There's two different answers to this question. One is this is complicated with Conda. If you have different, so if you have conflicts of versions, that is always difficult to solve. But there's always a possibility. For example, think about GROMACS. In GROMACS, we can have our own version of GROMACS in the workflow that is going to be installed by default when you type Conda install BioExcel GROMACS, for example. But this will be using the GROMACS that is installed by the Conda, but you can also use the GROMACS that is installed in a different machine, which can have a different version. So imagine that you go to a supercomputer and they have the last GROMACS that is compatible and is optimized by the hardware in this supercomputer. You can still reproduce the workflow there, but using the binary that is inside the supercomputer and not the one that is installed by Conda. So if you have two different versions, you can use one in the environment and you can use another one that is installed in the same machine. There's one way to solve that. In one particular environment, if you have conflicts of dependencies, you cannot solve it. No questions? Well, remember that there's the Google Doc also, and you can ask questions there. also in an anonymous way. That's always nice.
I can
Yeah.
The file that you are showing at the first, not the PDF, right? But you show another.
The document is also is linked in the Slack. It should be linked in the Slack channel.
Like in the Slack.
Yes.
Sorry.
In the Slack, this one.
PDF. Oh, okay. Okay. I can find now.
It's here. Okay, so if there are no more questions, I'm going to present in just 15 minutes a bit about what we've done using the library in the past years in the BioExcel Center of Excellence. We started with the idea of this helping the community on making our workflows more reproducible and more fair. And we have ended up with something like this, which is quite a large ecosystem of different tools surrounding this library. Tools like, for example, web applications with graphical user interfaces to use the workflows, these demonstration workflows, this collection that we have using a web server or using programmatic access or using different graphical user interfaces, workflow managers like Galaxy or 9 that you probably have heard about, describing the workflow with common workflow language that is, again, something that Elixir is pushing for, or going to HPC and try to deploy that in many different cores. I'm going to explain you a couple of these today, and I choose the one is the Jupyter Notebook because it's the one that we are using still today to start developing our workflows, and it's the one that we are going to use in the hands-on session after this. And then a bit more about what we call pre-exascale workflows, which is using scalability, enabling scalability using the library in supercomputers. So for the first one, the Jupyter Notebooks, how many of you are familiar with Jupyter Notebooks? Raise your hand. More than with the Conda? Okay, that's half of the people, so okay, that's fantastic. I love Jupyter Notebooks, but this is something personal, and I love them because in general, I think that they are fantastic for training. Like the hands-on session that we are going to have today, if everything works, I think there is a fantastic platform for you to follow all the steps of the workflow one by one, to interactively modify the parameters, rerun the cell, look at the intermediate results, what is this cell generating, if this is correct or not, it's fantastic. There's also the possibility to run it in my binder, but this is something that we can talk about in the hands-on session. But in particular for the BioExcel building blocks, it's a fantastic tool also to starting to be familiar with the syntax, this importing the module, modifying inputs, outputs, and parameters, and launching. Once you have done this 3 times, you already know how to work with BioExcel building blocks because it's exactly the same with different building blocks, but it's exactly the same syntax. Then you will learn how to build that using just copy-paste from the documentation, and you will learn how to package your workflow using this Conda YAML file, which is the environment. So for me, it's fantastic. And we are going to use this one. As a homework, you can take a look at the collection of workflows that we have in the website. Again, we started with one, and I don't know how we ended up with all of these. But they are showing the power of the library somehow because you can see all the different types of tools and workflows that we can produce. They are transversal, generic. They are not really specific for one particular project, but they can be used for many different scientific projects. But, and this is important, and this is something that a reviewer of the last paper that we published told us, and I completely agree with him or her, they are for educational purposes. They are not for production uses. And sometimes the user takes one of these and told us, okay, but I cannot use this to run 1 microsecond of simulation. Yes, you cannot, because this is just for you to see how you can build your workflow, and then you can extend everything and you can add a new building block, for example, and extend the simulation. But these are Jupyter Notebooks prepared to be run in something like a hands-on session, 1 hour, 2 hours at least maximum. So educational purposes. We are going to use the Jupyter this afternoon. And I forgot to tell you, but I think that there's a slide about this, sorry. Yeah, I think we have a slide about this. So it's not just Jupyter, you also have the possibility to deploy that in Google Colab now. So if you want to try, just go to the website. I think that it's in the launch button. You can launch directly the workflow in Google Colab. I was telling you about the uniformity and the syntax of the building blocks on how to import, define inputs, outputs, and properties and launch the building block. But we really, really like uniformity. So all the different workflows that we have in this collection also have this kind of uniform syntax. They have the header with information about the workflow, settings about information about the building blocks that are used, modules of the building blocks that are used, libraries that we use in the notebook, how to install and launch the Jupyter in a different computer. Remember reproducibility. This is all that you need to reproduce that in a different computer. And I recommend you to try it. I'm not saying this is going to work everywhere in all the computers in the world. I know Conda is not working everywhere, but try it because the reproducibility is really fantastic. Just 5 different lines, command lines. And then the steps of the whole workflow. Once inside the workflow, again, uniform syntax. We have a process where we have documentation about this is what we are going to do in the next cell, execution of the building block, and then inspection of the results. We try to do exactly the same syntax everywhere in all the different workflows. Again, I recommend you to take a look at the workflows after the school. And here is the uniformity, the uniform syntax that I was explaining you before inside the execution of the building block. This is something that we are going to see in the hands-on session after that. This is just an example of PDB2GMX, something that you all used yesterday in the hands-on session, in the GROMACS hands-on session. Information about this is what I'm going to do here. So PDB2GMX, generating a topology using GROMACS with this particular force field, with this particular water type. This is a link to the documentation of the particular PDB2GMX module where you can find information about which are the input and output mandatory files that you need to define, also the properties that are compatible. Here is the cell, and after that, the execution cell, and after that, the inspection of the results. All of this inside the Jupyter Notebook. And this is NGL view. It's one of, I don't know if you're familiar with that, but it's a tool. We're going to use it also this afternoon that lets you visualize in 3D the molecules inside the notebook. We also have inspection like this, a bit of Python that you can always integrate into Jupyter Notebooks. If you have, in this case, for example, the Plotly library as a dependency in the workflow, you can do something like this and plot 2D values like this one that are an energy minimization using GROMACS. And this is something that I already told you, but just as a reminder, you can build this YAML file. And with this YAML file, if you start building your Jupyter Notebook, and then you build this YAML file, and you put everything in a GitHub repository, this is exactly what we are doing. Then you can directly go to this binder website. You can put here your GitHub repo, the URL of the GitHub repo, and this will automatically deploy your Jupyter Notebook with all the dependencies already installed for you in a cloud environment. You don't know where, but the Jupyter is there for you. They don't have many resources, of course, because this is a free tool. But again, it's something that I encourage you to try. You can do the same with Google Colab. If you have all of this in your GitHub repository, you can use Google Colab to. You will need to add a cell, a special cell that you just can copy from our workflows at the beginning of the Jupyter Notebooks. And there's everything that you need. And of course, you can always install and launch the workflow in your own machine. And for that, again, 5 very easy command line, cloning the GitHub repository, creating the environment in Conda, activating this environment, and then running the Jupyter Notebook. It's everything that you need. You can do that in the website. As I was telling you before, there's a launch button for all the different workflows on our collection, and you can just click on this and try if this is working. Sometimes it's not working because Binder or Colab, most of the cases is Binder, is not working properly, but most of the times the Jupyter Notebook can be deployed for you. And again, this is the collection, and we are going to use this one for the hands-on session after that. All of this is, or at least we try to summarize all of this in this plus computational biology, which is a special education section. So all the different technologies and all the process that we are following is here summarized for you if you are interested. Now, I only have 5 minutes, but if you don't mind, I want to just introduce how we are using these workflows in supercomputer. And for that, basically, if you're not familiar with Jupyter, you probably don't know about this, but you can, from a Jupyter notebook, you can just download it as a Python script, and then you can just run Python and the Python script that you have downloaded, and this works. Now, of course, it has these advantages. The graphical cells, of course, they are not showing. You are losing the interactivity of modifying the parameters at the same time that you are running the different cells, but you are gaining high throughput. You have a Python script, you can run it as many times as you want in a command line. The point is that if you want to modify the parameters inside the Python script, you need to modify this Python script, and this is not convenient. So for that, we decided to integrate inside the library something that splits the workflow in two. The script is one of the file, and then the inputs, outputs, and properties that I was telling you before, it's in a different independent file, which is a YAML formatted file. With this, we can modify any kind of parameters that you can think about without having to change the Python script. And for example, in a very easy to understand, if you are interested in running or modeling different mutations on a protein, for example, you have a list. This is the YAML file. You have a list of 3 different mutations. And this is the Python script with the 4 in Python on all the different mutations, right? That is taken from this. You just need to modify this input structure and the input list of mutations, but you can use the same Python script, and then you can run another bunch of mutations in a command line way, in a high throughput way. And this has something integrated that to me is really nice. It seems really easy, but it's really nice, which is the hierarchy of folders. So when you run the Python script, in this case, when you have different mutations, if we take a look at the Python script, you have 2 different building blocks at the beginning that downloads the PDF file and fix the side chains of the PDF files, and then you start with a loop on the different mutations, right? So you have a main folder here, which is the result of the workflow. Inside this workflow, you have step 1 and step 2, 2 different folders with the outputs of these 2 first building blocks. And then we have 3 different folders with the 3 mutations. Inside each of the mutation, there's the rest of the building blocks that are inside the loop of the Python loop. So all of the hierarchy of folders are done directly by the library. You don't need to modify anything. And on top of that, if you allow me like 5 or 10 more minutes, on top of that, what we are doing to go to the HPC machines and explore this scalability is to add workflow managers that are focused on HPC. And for this, we are working with the Barcelona Supercomputing Center. They have one particular workflow manager that is called PyComs. And what this PyComs is doing is something as easy as that. Imagine that we have the Python script that I showed you before, a loop on different mutations. PyComs is directly identifying that. It's reading the Python script and it's identifying, okay, this loop here, it has 5 different branches that are completely independent. So I can run the mutation and all the different steps of setup with this modeled mutation structure, but I can run all these 5 mutations at the same time because they are completely independent. So PyComs is doing that for us, and it's running all of these in parallel in as many nodes as we have allocated in the supercomputer. And for that, I'm going to give you an example of how are we using that in real scientific projects, very quick. I'm sure you all know this picture here. This is a spike protein on the COVID, on the SARS-CoV-2 virus. This part here is the RBD receptor binding domain that you know that it is opening. It changes the conformation to start the infection. This is the angiotensin converting enzyme 2 in the surface of a human cell. This is how SARS-CoV-2 starts the infection. This is the surface of receptor binding domain. And at that moment, just in the middle of the lockdown, everybody was looking at the effect of the mutations on the surface of the receptor binding domain. And that's what we decided to do also using these tools. I had a really nice month in lockdown at home trying to implement this that Sudarshan is going to show you, I guess, this in the lecture after that. But this is the alchemical free energy calculation on relative protein binding free energies using GROMACS and PMX. Basically, we are trying to solve this thermodynamic cycle here. We are basically trying to solve the delta G4 and delta G1, and then from the subtraction of this, we obtain the delta G. That basically is giving us the information about, okay, if in the surface of RBD, I'm changing one residue by another, is this going to be more effective or less than the previous virus, right? So for that, in the technical part, we needed to run this equilibrium MD from nanosecond to microsecond from the wild type of the receptor binding domain, the same for the mutation of the RBD. Then we took the complex that was at that moment was already there in the PDB. We also ran for the wild type of the complex and the same for the mutant of the complex, equilibrium simulations. And from these four MD simulations, we ran as many thermodynamic integrations as we could, going from one state to the other. That means the alchemical mutation from this residue to the other one, forward and reverse. And we collected all the information, the work information in 2 different histograms. I know that it's really fast. I know that it's complicated. If you have questions, Sudarshan is the guy for that. But if you take the intersection of this and you apply some theorem, you get the delta G that you can then take the delta G at the end. For us, what that means is that we had to run MD simulations. We had to mutate different residues. We have to run as many thermodynamic integrations as possible, forward and reverse. And we ended up doing something like 1,000 independent short MD thermodynamic integrations between the different equilibrium MD simulations with using Mare Nostrum 4 at the moment at Varsovia Supercomputing Center. And that is something that I extracted that day. This is, for example, just an example to show you one single job, 48 nodes in the supercomputer. And all of this is using the library. I'm not lying. So this is the BioExcelBuildingBlocks library coupled to the PyComs workflow manager. And in just 8 hours, we obtained the equilibrium, the ones, the arrow ones, for a set of 12 different mutations. And then we use this to run the thermodynamic integration. And again, using 32 different nodes. And in this case, 1,000 thermodynamic integrations in just 5 hours, we got the results. At that moment, imagine that we needed the results as fast as possible. So we wanted to check if a particular mutation in the surface of the RBD was more effective or not. Now we know that there's many other key players in this, but at that moment, that was really important to have results in a short period of time. And this was fantastic. So we managed to publish this in this particular Wire review here. You can take a look if you want. But also one of the results that I think we obtained from this study is that quantitatively is really complicated to extract some conclusions using this delta G that we had. And this is something that we probably could discuss with Sudarshan here. But we thought that even qualitatively, we didn't have quantitatively, sorry, we didn't have a way to do that, to extract conclusions. Qualitatively, we could extract conclusions. So we decided to use the same kind of workflow with a different system, completely different, epidermal growth factor receptor. And in this case, we were looking, this is a very popular structure, protein that is related to different kinds of very aggressive cancers. So there's many different drugs on the market, but there is known that depending on the mutation on the different persons, they have resistance or they are more sensitive to this particular drug targets. So we decided to do exactly the same, use exactly the same workflow for that. And again, in this case, qualitatively, so we put a cutoff and say, okay, so negative ones should be more sensitive, I think it was. Yes, and positive ones should be more resistant to the different drugs. And we had 100% results. So we got all the different, if you look at we looked at the literature, and this is something that we work with Nostrum Biodiscovery, the pharmaceutical company. They helped us identifying this in the literature. And PMX was able to spot all of this. So which mutation for a particular patient was resistant, was adding resistance, and which one was adding sensitivity. And of course, now this is being applied for prediction of different resistance depending on the mutation. But this is just examples on how we are using these particular tools in science. Okay. Oh, I know I'm running out of time, and it's 5 past already, but just allow me the last slide. So I'm sure that you know that we have now an ecosystem of EuroHPC supercomputers. So yeah, this was an old feature that I liked the most, but this is the new one, many different ones, exascale ones now being built. And we should have access to these supercomputers, and we should have the possibility to keep running this kind of HPC workflows there. So we are now working with many different ideas in BioExcel, some of them related to neural network autoencoders that are really trendy nowadays. We are starting to develop the BioVP PyTorch module using all of this, integrating all of this. I don't have time to go into details on that, but one of the things that we are doing is try to reduce the noise between different trajectories with different mutations. Another thing that we are doing with these autoencoders is to try to extract automatically collective variables between transitions. We have a transition, coarse grain transition from one conformation to another. We extract the collective variables, and then we plug these collective variables to GROMACS and plumed. We run metadynamics, and we extract this pathway of free energy that identify intermediate conformations. Something like this is going to be run, of course, in these big supercomputers, and this is something that we are now working on. And finally, we are exploring the possibility to put together all these key core components in BioExcel, Haddock PMX, GROMACS, and also the building blocks library, wrapping everything and building these reproducible workflows with the antibody case that Alexander was explaining you yesterday. And the idea is to use this for training and for outreach also in the BioExcel, as we are doing today with the different workflows in the collection. As a summary, something important, at least to me, they are easy to build. It gives interoperability, everything that I have told you. I'm a really fan of the library, of course, because we are the main developers, but it's not magic. I need to tell you that. So Conda is not working everywhere. It's working fantastically well in most of the computers, but it's not working everywhere. That's one thing. And you still need to know about the tool that is wrapped. Of course, if you look at the documentation, for example, of GROMACS building block, you need to know what GROMACS is doing. So if you don't know about the different process that you need to set up the protein to start running a simulation, you cannot build a workflow with the building blocks. You need some knowledge behind that before. So it's not magic. It's not giving you the results directly. And you still need to build your own workflow. It's exactly the same that I was telling you. Okay, so after the coffee break, we are going to try to deploy a Jupyter notebook, one of them, the protein ligand complex here, and we are going to go cell by cell, all of us together. Questions?
Yes, question. So we might have online no questions. There are no online questions. Okay. So in person.
I was just trying to download this workflow, and then it says GROMACS 20 beats GROMACS 2022.
Yes.
Is it the only GROMACS version and can we switch around?
Yeah, it's what I was telling before. If you want to use a different GROMACS and you have access to a different GROMACS in a different machine, you can always just modify. There's one property that is common to all the different building blocks that is called binary path. So you just modify this property and you put the binary that is installed in the computer, and this is going to use the GROMACS that is installed in the computer. The reason that we have this 2022 is because we were waiting for the new one. in the next release of the building blocks, we hopefully will have the new one already as a dependency for the workflows. Because the new ones, they are working with the combination with GROMACS and Plumed, which is really interesting for us. But this is in the development, this is what they are deploying in the supercomputers, but this is not in the Conda package. This is a different part. So if they manage to produce this Conda package, then we are going to use this. And we are in contact, of course, with the developers, trying to push them. Yeah.
In different GROMACS versions, different commands they have.
Yeah.
May have changed the MD parameters, the commands of it. How can you manage the BioExcelBuildingBlocks change updating?
The thing is, when we deploy the new release that is hopefully is going to have the new GROMACS version, we will need to make sure that all of this is compatible yet. Everything that we have is compatible with the new version. For that, we have this continuous integration. We have automatic tests that we run every time we modify a building block and we push in GitHub. This is going to be deployed in some virtual machine and it's going to run all the tests. If something is wrong and is not compatible with this version, we will know, and then we will need to fix it. And then we can have two different versions. If in the Conda environment you fix one version of the GROMACS 2022, the previous version will be installed, not only the GROMACS part, but also the building blocks part. So the one that is compatible with this GROMACS will be installed. But if you fix the version of the new one, the new GROMACS will be installed and also the new building blocks will be installed. So this is again reproducibility. You can still reproduce the old one with the old versions of everything, but you can at the same time work with the new ones.
Any other questions?
So I did write on the document, but
yes.
First section you talked about the HTML for the protein I want to just if there's a label workflow for the membrane proteins.
Membrane proteins. It's not available, but it's something that we get as a feedback in many different workshops. So we are exploring this in many different ways. So yeah, we can talk about exactly what is the, or you can just type in the Google Doc, or you already did that already. Okay, so we can take a look and we can talk about this.
So I think we're done with general questions, and you have 20 more minutes to ask during the topic break.
Yeah, sure.
And the whole day to ask your questions. Thank you very much.
Okay, let's go. I'm not sharing what that's. Share. Okay, so let's start with the tutorial part, the hands-on session, the fun part. Just as a reminder, we are in the second part now. We have 1 hour and a half. The idea is to try to deploy one of these demonstration workflows that we have from our collection in the building blocks library and try to use the Jupyter notebook on the open on-demand platform connected to Truva. By the way, I want to thank now, before the session, to all the Truva system admins that helped me with the, let's see if it works. I hope that it works now after thanking them, but they helped me implement the kernel, the Python kernel that we need for the open on demand to be able to reproduce the workflow there. We are going to use this particular workflow from the website. All the information that you need is there. And here you have again a link. Remember that you have the PDF with all the information in the GitHub. But now, yes, this is exactly the same. This is what we are going to do, but we'll have time to that. I have many questions, very easy questions, don't worry, for you in this, to make a bit more interactive this session. I know about this one, because I have asked that before, but not about this. Have you ever used open on demand platform in a cluster, on a supercomputer, in a research institute? Yes? Can you raise your hand just to see? Okay. So most of you didn't. Okay, so it can be a bit of a challenge. Let's see what happens. I have slides, as you might already see in the in the PDF, about how to connect to this open on-demand platform in Truba. It's kind of easy, but just in case, I will be around the room to see if you are able to connect. Sudarshan is also helping me. He's really kind. He's always helping us. So he's going around the room too to try to help you. Remember, you should have the VPN activated. This is important. And then you have here a URL to connect directly to the open on-demand platform. You should see something like this. If you don't find something, just raise your hand. We are going to try to help you. But I think now it's clear so far. In the ARF menu, you should find the Jupyter Notebook BioExcel. Yes. And if you click and you can, I think by default, I don't know if it's 1 or 2, just put 2 just in case, because we have 1 hour and a half, and then click on launch. Everything clear so far? Okay. Okay, so do you have the PDF? Right, so next one. Yes. There's the link here. Oh, wow. But you can select, right? At least. No? You remember that IP assets? That's a good memory. No, the edge team one. It needs to be the edge team one. No, the edge team with your number, but and your.
I think he has not gone to the next step.
For the ones that are already here, you can click on connect to Jupyter if you are already here. So the first step is this one. You will need to wait a bit because this is going to be queued in the cluster of computers. And then once you have a resource allocated to you, it will open directly this part here and it will tell you you have one node with 4 cores that is running for you. And you just click on connect to Jupyter and then we will pass to the next slide. The ones that are quick, you have in the PDF, you can go slide by slide and go on if you want. You can find?
Everybody has already launched their.
Perfect, perfect. Tutorial, yes, the PDF tutorial. Yes, it's this one. And the link to the open on demand is this one. Yeah. ARF, BioExcel, you can know BioExcel. 2 hours because it's going to be killed if not. So now wait a bit. Okay, I think we are all on the same page now. This is the most complicated step of all. So once you are here, in this page here, I hope that you are all here. You can click on terminal and this will open a terminal for you, a new tab here. And in the new tab, you need to copy this line that you have in the PDF. For the ones that are familiar with GitHub repos, this is just going to clone one of our repositories of one of our workflows, which is the one that we are going to use in the hands-on session. There's a reason that I leave this part for you, this step for you, and is that you can reproduce exactly the same step, just modifying this GitHub repo here for a different workflow from the collection of workflows, and that should work also. So you can clone a different workflow from the collection. Not all of them are working because the Conda environment that it's here doesn't have all the dependencies for all the workflows, but most of them should work. So if you want to play, and I don't know how many days you are going to have this user account open. I don't know if there's somebody from Trubac here. 2 days after this, after today. So you have 2 days to play a bit with that. Okay. But 1 or 2 days. What?
People are not able to copy.
Oh, yes, I can put that.
You can put it in the slide.
Yes, of course.
So he's posting the link in Slack, which you can copy. You can go ahead. Yeah, so
So it seems that this line cannot be copied from the PDF. You have it in the Slack channel now, if it's the correct one.
Also, it's in through the GitHub page, they can just see from there as well. The way you see the
I don't get that.
In the Truba GitHub page, the link is also
yeah.
from there.
Okay, okay. So you can copy from the PDF there. Yes, you need the Git clone. So you can select now. I pasted it in Slack. If you have Slack, you just copy and paste the lines. If you don't have it open, we can. Yeah, but you need to connect to the east one, and it's a process. It's a process. Right? Okay. No, but I can.
Here,
You can do it. You can do it. I'm just trying to make it easier for you. And now you copy it in I don't know where the open on demand is. Here. No, in the Jupyter. No, sorry, in the terminal. Yes, this one. So you copy it.
but it's not
the eye is a different eye. Can you change the eye? Sorry, that happened yesterday to me. I tried to make deer and it was impossible because the eye was a different one. Okay. Okay. It works. Now it's here. Good.
Okay,
Now I
thank
can
you.
open it for you now, and there's a step that you will not need to do. It's finding where the notebook is. Okay, I hope that all of you, no, all of you have cloned the repo already? Good. So next step is navigate a bit to the file explorer till you find the notebook. And that is this path, right? This folder, and notebooks, and you will find the notebook there. It's a bit hidden, I know, but this is exactly the same for all the workflows. So if you know that, you can be able to reproduce all the other workflows, right? And you have a workflow already there. Perfect. Can you run some of the cells and see if everything works? Yeah, that's a good one. But for the ones that already know, at least how to run a cell. Are we all there? Yeah. No, but you don't need that. It's just for collab. No, don't worry. It's okay. No, just don't run these cells. Just click on this one and start running this one, and forget that. Yes, and forget about the two previous ones. Yeah. Okay, so that works because just importing, and here just click on this one and run again. Okay, now it's working. These ones are for the Colab compatibility, Google Colab. Yes. That's fantastic. And now we need to find, can I? Yes, you might. So you have it here now because it's cloned here 9 seconds ago, you see? Something wrong. And you click here, notebooks, and the notebook is here. And then it opens the notebook. And let's see if the cell works. The first one. Okay, so you can work it with, you can run it with display, or you can run it with the shift enter. Now we are going to do that step by step. Yes, good. Everything fine? So please, if any of you has still problems with this, raise your hand. I think that now we all have the Jupyter Notebook there open, so we can start running the cells and looking at the workflow. Good, let's go. So yeah, remember this is using the Truva computational resources. So thanks again for all of this. It's amazing for a workflow like workshop like this to do that, to be able to do that. Okay, so I have some slides here for you. I was just telling you this is using Truva resources because we are lucky, but at home, if you want to do that, remember that you can still do that, but you need to install Conda. It's the only dependency that you need, and then just follow the installation and launch command lines that you have in all the different workflows from the library, right? Exactly the same for all of them. Questions to start with the first one. To start with the hands-on session. Have you ever run setup? Have you ever run a setup process for an MD simulation using GROMACS? I know that yesterday you did something with PDB to GMF, you surveyed the system. Have you, before that, are you familiar with GROMACS? Have you ever did that before? Okay, not all of you. So okay, I'll try to go then a bit more slow on the process, on different parts. And in a different engine, and the engine like Amber and MD, I know Desmond, there's one here for Desmond. Okay, so more, okay. That means that you know about all this process, even if you don't know about GROMACS, that's good. And for a protein and a ligand complex, how many of you? Okay, that's not bad, that's not bad, good. So you know most of that. This is what the different steps of the workflow that we are going to see now. Forget about the first one, it's done. We are going to download and fix the structure. I will tell you something about this. We are going to generate the topologies, 2 different topologies, one for the protein, one for the small molecule. Then we are going to put all of them together. This is GROMACS. Generating the restraints for the small molecule so that it doesn't go away when we start the simulation, and run all the setup process with the box, with the solvent molecules, with the ions and everything, and then just run some basic analysis. All of this is integrated in this workflow, and all of this is using the library as I was explaining in the lecture. I think that this is for, no, this is for the next one. So we can start with the Jupyter Notebook. I ran all the notebook before just in case something happened to have all the outputs, but in any case, oh, sorry, starting from the beginning. You see that? Yes. So remember the uniformity that we try to follow in all the different workflows that we have. Here you can see a header, which basically explains what the workflow is doing. So it's a process of setting up a simulation system containing a protein with a ligand. You have the link to the PDB protein. You have the link to the PDB ligand, the structure of the small molecule. You have all the building blocks that are going to be used in the workflow, which of course are part of the YAML file that lets you reproduce the workflow in a different computer, which by the way, is part of the package that you have cloned with the GitHub repo. So if you navigate a bit in the file explorer, you will find the YAML file with all this information. There's also auxiliary libraries that we are going to use for the intermediate results, for the inspection of the intermediate results, NGLView, for example, the 3D visualizer, protein, macromolecular protein 3D visualizer, but also simple track to see the trajectory at the end, if we are lucky, and you reach the end of the workflow. And then you have the lines to install and launch the workflow in your computer, and the steps, the ones that I already told you. We are going to go one by one for these steps. There's one part here of the workflow that is initialized in Colab. You don't need to run these ones because this is only for Google Colab. This is what makes these workflows compatible, notebooks compatible, both with Jupyter Notebook and also with Google Colab. Forget about this. In this case, we can go directly to the input parameters. And as Sudarshan kindly said, I need to remember that when you want to run one of these cells, if you're not familiar with Jupyter Notebook, there's a play button here to run the cell. If you want, you have a short key that is Shift and Enter. You can do Shift and Enter, and the cell is going to be run. As you can see, this is Python. We are just importing the auxiliary libraries that we are using. Those are the input parameters of the workflow, PDB file of the protein ligand complex. In this case, we have the experimental complex there, the small molecule 3-letter code that we are going to use, and the molecular charge for the parameterization part of the small molecule. Those are the only 3 inputs of the whole workflow. When you run this is basically assigning to this Python variable, this string, nothing new. I hope that you're all familiar with Python. If not, just ask if there's something that is strange and you don't understand. First cell that we are going to use, the first building block is fetching a PDB structure. So just downloading a PDB structure from the PDB databank. Remember the uniform syntax, so information about what we are going to do in the next cell. So downloading a PDB structure, nothing else. And then we are going to split the molecule in 3 different files. We are going to split the molecule in the protein, the small molecule, which is the one, in the complex file with the protein and the small molecule. The thing is, if you go, we can do that after that, but if you go and see this particular PDB structure, you will see that it's not just the protein and a small molecule. There is 3 different small molecules, and we just want one of these molecules for our MD simulation. So we need to get rid of the other one. And this is basically what this is doing. This can be also done in just one command line using the PDB tools that Alex was explaining to you yesterday. So they are really useful for this kind of things. But in this case, just for demonstration purposes, we are going to use the BioExcel building blocks. With these ones here, the PDB that downloads the PDB, the extract heteroatoms that extract the heteroatoms, the small molecules of the PDB, extract molecule to extract a chain, I think, and cut PDB to join together two different PDBs in one single PDB. So downloading the structure, remember, very easy. Importing the building block, defining inputs, outputs, and properties. And that means I'm going to define an output file that is going to be called the PDB code.oric.pdb, just a string using the variable that we have initialized at the beginning, right? Then in the properties, I will put this is the PDB code that I want, and this is some filter. Now you're wondering what the hell is this, of course, but when you click here, remember you have the documentation for each of the building blocks. So here you have output PDB path is the mandatory output, in this case that you need to define. There's no input, so you don't need to define any input because the input is taken from this PDB code, which is a property. You just put the PDB code here, 4 letters, and this is going to download. And the filter, you can see the information. This is the array of groups from the tags, if you're familiar with the PDB file, to be kept. If you put false, I think that is false. In the example, it's going to take everything. Back to the workflow, I guess that you have already run this one, and you have this information here that is telling you I'm using this particular building block with this version. Again, reproducibility, you can use a different version of the workflow with different version of the building blocks, but this is going to be written in the log file so that you see. Is downloading the PDB from this website here, and is writing the PDB to this particular file. Easy, I know, it's easy, it's just downloading the file. But here I have one question that this is not the first time we are doing this workflow. We are showing this workflow in a workshop. And one of the questions that I get multiple times is, okay, you are downloading a PDB file, but what if I want to use my own PDB file? I guess that you can imagine that it's just modifying, instead of downloading, you can use one path from your machine and just put this path. Instead of, let's do that. Instead of using this, if you don't follow, please tell me. And at the same time, I'm going to show you a bit about Jupyter Notebook for the ones that are not familiar with this. How to create a new cell, very easy. There's a plus here, symbol. So you click on plus and there's a new cell here, right? And I can put something like this. And this is going to, this is going to assign to this Python variable, for example, a path, dot missing, a path to your own machine, to a PDB file that you have in your own machine, so that from now on, this downloaded PDB will be this PDB and not the one that we have downloaded from the database. So this is the way that you just use this workflow with a particular file from your machine. Okay. After that, you can click on, you can run this already, and this is doing 3 different, it's running 3 different building blocks, as you can see. It is, I think that it's a comment somewhere, extracting the protein, the small molecule, and the complex to 3 different files. Again, if you look at the documentation, you will see how to define this property to say, okay, the only small molecule that I'm interested in is this one here. We are going to see the structure after that, but this is the code that we know that the ligand that we are interested in has. Then we extract the heteroatoms, the molecule, and we put together the 2 different files. We are going to see that now. If you click on run, and you're going to see all of this information, log files here. Those are the log files of the tool that is being wrapped. In this case, there's an on-house tool, as you can see here, that is called structure checking utility, that basically is looking at many different things in the PDB, but in this case, it's just extracting a part of the PDB. And remember about the uniform syntax, we had a cell about information that, by the way, I can tell you that to do this kind of information, like this one that you can see here, documentation inside the Jupyter Notebook, you can change here the cell. Instead of code, you can tell Jupyter Notebook that you want Markdown, and then you can do something like this. Of course, you need to know a bit of Markdown, but this is a title. And if you run the cell, it's going to be converted in a title. And this is how we are generating this documentation, right? So then, if you are here and you can run that with me, and I really like this part of the Jupyter Notebook, we can inspect, right? The intermediate results. So this is the first file that we generated, which is the protein, nothing else, just the protein. Second one, small molecule, just the small molecule, nothing else. And third one, the protein with the small molecule here. If you're not familiar with NGL, clicking with the mouse, you can rotate. And then with the wheel, you can zoom in and out. Right? I'm going to do something a bit more complicated now for you to see how this works. Let's see if you can follow me. So I'm going to take this, just a part of the inspection cell. Is the one that is telling NGL to visualize a small molecule. I'm going to copy that. I'm going to go up. Just right after the downloading of the PDB, I'm going to paste this here. Why the output is 0? Is the exit 0 is just the code of everything worked. If the output is something,
it's not false.
It's not false, it's just a standard. I know.
Yeah.
If it's not 0, something went wrong. Okay, so I just copied this here just to show you that you can do something as easy as that. So copy and paste a part of the cell and modify, instead of ligand file, I want to see the original one, right? If you're following me, this is a PDB file, the original PDB file. Let's make this bigger. And you see that it's not just the protein and the small molecule, it's the protein, is water molecules surrounding this. This is the crystal structure, crystallographic structure. There's also the some small molecules, not just one that you cannot see, but maybe we can put that as a selection. Let me copy a selection. This is just to see, for you to see that we can do something like this. Where is the selection? Selection, yes. You still see the water molecules that are really big. But you can see there's a small molecule here. Oh, sorry, it's not. Yes, you see there is a small molecule here, an extra small molecule, something for the crystal structure, for example. Using the building blocks to extract the molecule and extract the small molecule, we have just get rid of all of these, all the water molecules and the ones that we didn't want for the system. So we ended up having the system that we wanted, which is just a protein with a small molecule. Is everybody following? Yes. Questions?
Yeah, I didn't run the same comment, but I'm just viewing the plugin.
Have you modified the input to this one here? should be the downloaded PDB.
Panel editing that you are doing. So
But this is just an example. It's not, you know, it was just for you to see that we can do something like this. Yes. Okay, so what I did is just to take this. Copy. Then move that where we downloaded the file. Just after downloading the file. New cell. Oh. Oh, yeah. Thanks.
Yeah.
It's just an example. Yeah. It's just doing it really quick if I can. Here to this, and then instead of the legal file, I just put that down. This, another. And if you execute that, you will see this is the original one. But you can see it's just copying and pasting and playing a bit. Yeah.
Hope to see you again.
Yeah, okay. It's just copying. Copy this part here, for example. So itself is the NGL. Paste it here. And modify this, which is the input. So we are telling NGL to display the download PDB file, which is the one that we have just downloaded. If you have run it, if you don't have run it, you need to run it. Remember, you need to run. You run this one because there's a number here. Then you need to run this one like this. It's going to download the PDB. Then you run this one, and this is displayed. And then you can run the other ones, right? Yeah. Okay, moving on. Yes. Moving on with the workflow, we have another step of the workflow that is fixing the protein structure. And you can see again information about checking and fixing the protein structure if needed. That's something that we typically don't do, but this is really, really important. So for example, missing backbone atoms, missing side chain atoms, these kind of things is going to have a big impact on the MD simulation. Actually, if you have missing side chains, the MD engines will try to reproduce and predict where these missing side chain atoms are. But if you have missing backbone atoms, it's a bit more complicated for them. They will tell you a big warning saying, be careful with this. This building block here is not fixing everything for you, but it's trying to fix, or at least it's warning and telling you what the possible problems in your protein system are. I wanted to, we don't have much time, but I wanted to show you, I think in the PDF, you have a link. It's not for now because we don't have time, but I just wanted to show you. We have a website. Remember the ecosystem that we generated surrounding the BioBB library? This is one website that we generated. With this website, you can provide a PDB structure, and the website is checking, is using the building block that we have just used in the workflow. The link for the ones that want to visit the website is in the PDF. But this is checking all of this that you see here. So the chains, the alternative locations, the small molecules, the heteroatoms in the structure, the amide, incorrect amide assignment. So for example, this is something that nobody looks at, but there is an amide here, this group here, and you see that there is a oxygen atom that even myself, that I'm a computer scientist, I see that maybe in front of another oxygen atom, negative is something that they don't like to be, but this is an amide, and you remember that in when they solve the structure by crystallography, they don't see the difference between this and this, and you can swap that, and basically this is what's happening here. In this, you can fix it, you just swap the nitrogen by the oxygen, but this is something that you should take a look All of these possibilities here. There's also the polar clashes like this one. Again, oxygen, oxygen. I don't know if you're seeing it. Yes. You know, in this case, there's a nitrogen atom here. So, okay, maybe it's all right, but there is an oxygen that is quite near. This kind of things is something that you can use a tool. This is not the only one. There are many tools like this that you can use for this. But just remember, it's important before starting a simulation, remember this rubbish in, rubbish out. It's important to take a look at the structure and the system before running for days in a supercomputer one simulation. Okay, so you can play with the web server if you want after that. So we fix the sidechain. In this case, I think that there's a sentence in the log file that is telling you that there's nothing to be fixed, no residues missing or unknown sidechain atoms, and the structure has not been modified just because there was no problem with the structure, apart from the ones that we've seen in the website that are not so important. Okay. Have you been following so far? I think that we have questions, but maybe I will skip them, but yes.
Chains. Is there any script for this?
Yes, for the missing sidechain atoms, the MD engines again did good work. So for example, PDB2GMX is able to do that. But for the missing backbone atoms, you need to model them. So for
model for this.
Yeah, modeler, for example. Yeah. Yes. So we have a module for that too. But remember, yes, there's a building block for that. But remember, you need a license for this. So we will ask you for a license to run modeler because it is required. Everybody knows the code. Modeler is there. Yes. Swiss model is another one. Yes. Yeah. Yes. That was for the other one, but I think we are now going to parameterize the small molecule. So the question is the second one. Have we ever parameterized the small molecule before? Not many of you. Okay. Okay. So we are going to use in this workflow the same building blocks that I showed you before in the. I have to skip one. I have missed one because this is the topology of the protein. Let's do the topology of the protein first. Sorry about this. Remember that I was telling you at the beginning that we were going to work with the protein on one hand and with the small molecule on the other hand. So let's start with the protein. We try to fix the side chain missing atoms. We try to see if there was something wrong. And after that, we need to create the topology. And for that, we use PDB2GMX, which is exactly the same tool that you used yesterday in the GROMACS hands-on session. And this is what I showed you in the lecture. So you already know information about which is the force field that we are using, information about the water type. We run this building block, which is the PDB2GMX with the force field and the water type. And then this generates topology for the protein, right? And after having the topology for the protein, and you can see at the, I mean, this is not a GROMACS tutorial, but you can take a look at the logs of the GROMACS PDB2GMX to see if any missing sidechain atoms have been added, if there was some disulfide bond to covalently bond, and all of this information will be here. Also the different protonation states of the histidines like this one, all of this information is written in the log file. Now, we are going to the small molecule parameterization, and we are going to use the same building blocks that I showed you in the lecture, right? So actually not exactly the same. We are going to add the hydrogens with a different tool. And this is again to show you that we can use different tools to do exactly the same task. In this case, in the lecture, I showed you that with OpenBubble, you can add hydrogen atoms to the small molecule, but we also have this reduce tool, which comes from the Amber Tools package. And we have a building block for that in the BioBB chemistry module that adds the hydrogen atoms to small molecules too, the same way that OpenBubble. So we are using this one. Then we are minimizing the hydrogen atoms that are placed by reduce, yes?
That's a question, Adam. So how do you change the protonation state? So now it assigns the protonation state by default.
Yes. That's
how
what
can we modify?
You cannot, well, you can modify the charge, and depending on the charge, you can also modify, but not in this case. I don't remember if this reduce or the open bubble, one of them, I think that lets you modify something, but in any case, they are not perfect with that. So there are different tools to do this, and that's what I tried to say during the lecture, but most of them require a license. So this is something to run in a high throughput way, but if you want to really take a look properly at the protonation state, you should take a look also at these different tools, like Chemaxon, like the one that is leak prep that it's in Schrodinger, these ones.
Then likewise, if you want to start from a looking snapshot, looking pulse, then the same thing, because there we just define the crystal structure ID, PDB ID.
It's the same. It's the same, but you can always run these tools before and then use the PDB with the correct protonation states as an input. It's a step before that. It's a previous step before the workflow. But yes, there's nothing integrated in the building blocks now that assigns properly protonation states. Okay, so in this case, we are assigning these hydrogen atoms in a kind of a roughly way with reduce, minimizing the hydrogen with label minimize, these ones here, and then generating the parameters for GROMACS in this case, because we want to run this using GROMACS, that's the GMX. So we have AC pipe params for GMX, AC pipe params for Amber, and for different ND engines. This is for GROMACS. And if you run these 3 different cells, so step 1, add hydrogen atoms. Step 2, energy minimization of the hydrogen atoms. Before running the AC pipe to generate the parameters, let's take a look at what happened. Again, inspection of results, intermediate results. This is the original structure taken from the PDB. This is the one with the hydrogen atoms that reduce, in this case, added. And this one is the one that has passed through an energetic minimization. Don't tell me why this hydroxyl here, the hydrogen atom is pointed like this. I'm not a chemist, but this is what this particular tool is doing. And this is important because these coordinates of the atoms are the ones that we are going to use in the MD simulation after that. So of course, at the beginning of the minimization step of once we had the whole system assembled, this is going to be corrected in any case, but it's always important to have the correct coordinates at the beginning.
Does this minimization occurs with a code that finds the nearest minimum or makes a...
You mean the small molecule one or the one with the... Sorry?
Ligand.
The small molecule one. Yeah, this is just the steepest descent. Is really a very small energy minimization.
Search for the whole conformation.
No, not in this case. You see the difference is from this to this one.
Yes, I see.
And you see that? Yes. Hope that you are here. Are all here in the same? Okay. Yes. Yes. Good. And the last step of this is generate the parameters with the AC pipe, right? So we took this. We take this one, the last structure with the hydrogen atoms, minimized. We use as an input. I think I don't have to repeat that, right? I'm importing the module, the building block in this case, defining inputs, outputs, and properties. This is the last time I'm going to say that, and then run the building block. Okay, so now we have the topology of the protein and the topology of the small molecule in 2 different files, separated files. Now, I think I have a question about this. I guess that you have been following, but are you familiar with the concept of restraints in MD? Second question, more or less. Restrain, how to restrain. And force field parameters, this is not so important for this workflow, but force field parameters. Okay, but you should if you're using MD, so okay, good. Now, I just wanted to ask you that because the next step is something that is not easy to understand, which is preparing the restraints of the ligand. And this is very specific for the GROMACS in this case. Amber has a different way to do that. Of course, you can do exactly the same with different MD engines, but in different ways. In this case, to generate ligand restraints in GROMACS, you know that you need to add, well, the ones familiar with GROMACS know that you need to add one or two different commands in the topology file saying this is going to be restricted in the simulation. This is what we are going to do now. Again, very specific for GROMACS, complicated to understand, don't worry about this. But what we are going to do is to create an index file, GROMACS NDX. The ones familiar with GROMACS, NDX is an index file that is just a set of numbers saying this is the atom number 2, 3, 4, 5. This is a selection that then we are going to use to restrain just this selection of the system. Our selection is the small molecules. And this is why we are doing that in the topology of the small molecule. We are generating an index file with this particular building block here. You just run the building block. This is wrapping. I didn't tell you that, but in the log file, you can see exactly the command line that we are running. So this is the command line that we are running inside behind the scenes. GMX, make NDX, so make index. It's one of the tools that is included in the GMX engine, ND engine. So we run that. You should know about how to define that this is the selection that I want. There is, you cannot see probably the system, but without the hydrogen atoms. That means all the small molecule atoms, but without the heavy atoms of the small molecule. This is the way to tell GROMACS, please select only these atoms and make an index file or a group in the index file with this selection. And then generate the position restraints file that also GROMACS needs. And this is where you define the force constant X, Y, and Z Cartesian coordinates force constant for this particular selection of atoms. Complicated, again, this is GROMACS specific. Don't worry if you don't follow these two different steps. We are going to use that in any case in the workflow. Now, this is important. We are going to create a complex file, protein and small molecule. Now, the question that I get always when I reach this point of the workflow is, okay, we already had the complex before, right? So we downloaded the complex from the from the PDB database. Why do we need to create a new one now? There's many things that have changed since the beginning. We have extracted just the protein and the small molecule. We removed the water molecules. We removed the extra small molecules. We have added extra, in this case, no, but maybe extra side chain atoms that were missing. We have added all the hydrogen atoms were not there at the beginning. So these structures that we have here are completely different from the ones that we started the workflow with. So that's why we need to generate a new one. And this is very important because for the MD engines, the structure needs to match the topology file. So all the atoms that we have in the structure, in this structure that we are going to create now, need to match all the same order, the same atoms that the topology files that we have just created. We have created the topology files of GROMACS for the protein and also the one for the small molecule with AC pipe. Okay, so this is just taking the structure from one and the other, put them together, and this structure matches the topology files that we have just created. This is very important. And for these building blocks, again, we have all of this before, but we have them in different formats. We have a growth file. We have a growth file with hydrogens. We need to convert it to PDB for the protein in this case. This is one building block that lets you do that. It's using one tool from GROMACS that is trajectory convert for a particular structure. We are converting just the structure from GROMACS to PDB. We are doing the same with the small molecule. There is also a growth file that is generated by AC pipe, the one that matches the topology. We convert it to PDB, and then we put them together. The structure of the PDB of the protein and the PDB of the small molecule. If you run all of this, and I hope that we have an inspection somewhere. Oh, and we have the topology file before inspecting you can inspect. You can do exactly the same as I did before, just copy and paste the NGL view commands to inspect what happened with this protein ligand complex that we have just generated, but just in case, I'm sure that there's another cell to inspect after that. Now the topology. So now we have the complex and we have the topology for the protein and the topology for the small molecule, and we need to put them together again. And again, difference between Amber or NAMD or different MD engines and GROMACS. How can we put these two topologies together? And the best practices from the GROMACS side, unless Nandan tells something different, is you open the topology and you write it manually. Well, for the high throughput, this is complicated. You cannot open and write it, or you can just modify the, sorry?
In the older times, we did preparation.
Yes. Writing, editing the topology file, right? Yes. As far as I know, there's nothing yet in the GROMACS package to append a ligand to the topology. You need to do it manually. That's why we decided to do something like this, and we generate a new building block that is called append ligand. We tend to not do that. We just wrapping tools that are existing tools, but in this case, if we wanted to do this workflow, we needed something like this, so we decided to do that. It's the only one that we have that we do something internally in the building blocks, which is basically open the topology, editing the topology, adding this small molecule there. It just works for one. It is not working for more than one, so it's just something to, okay, yeah. Let's wait for GROMACS to have a tool to do that. We are not going to do, but in this case, it's just for one. Yes?
It's that hard to read the script to do that, because what you are saying to me, you can also say to
it's harder than you think, because you need to know about where to put these lines, what to modify to the topology, and it depends on the solvent that you have, on all the different objects that you have in the topology. You can have a discussion with Nandan about this. It's not me that I generated the format of GROMACS topology. It's harder than you expect, I can tell you. But in this case, this is opening the topology and adding one single small molecule. And here, a kind of a trick is where we define the restrictions. So again, in GROMACS, where the restrictions are defined is in the topology. So where we place the atoms of the small molecule in the topology, we also need to place the position restrictions that will only be activated once we run the equilibration step. This is, again, for the people that know about GROMACS, very specific. But it's the only way to do that. The other way is manually, of course. Okay, so you run that. And now we are in a moment that we have finally, look at that, it's only that. So complicated, just the complex of the protein and the small molecule and the topology. We have the structure and the topology. Now we can start building all the systems. So creating the solvent box, adding the solvent molecules, adding the ionic molecules with different concentrations. And this is what we are going to do now. I'm supposed to finish now or in half an hour, I don't remember. In half an hour, oof. Okay. So from now on, it's kind of easy, should be kind of easy for you because now the system is prepared. It's just, again, creating the solvent box. We have the edit conf building block. You can run it if you want, trying to follow me. Again, you can modify the properties. You can modify the type of the box, the distance to the molecule. Remember, you have the documentation. If you click here, that will tell you the inputs, outputs, and properties that you can modify, which are linked to the tool that we are wrapping, of course.
The shape of the box, for example, here you choose octagonal.
Yes. Yes. Yeah. Yeah. Let's see that. If you click here in the, you see that? This is the documentation of the edit conf. And here you have a property that is called box type. By default is cubic, but then you can choose between the ones that are compatible with GROMACS. And if you look at the building block that we have for Amber, it's exactly the same, but with the properties that are only compatible with the Amber tool. So we create the solvent box. We fill the box with water molecules, easy, different building blocks, but just the same way of running. And once you get here, now we are going to take a look if that works. Is it working for you now? This? Yes, good. Okay. So this is again a nice way to see that everything is fine. We have the protein, we have the small molecule. You cannot see that maybe now. Yes. You have the small molecule here in the place that it should be. You have the protein and you have the water box.
It's not in the center of the.
It's not, but this is the visualization problem. If you put the cubic, you will see it just in the center. But if you put this, how is it? Is it octaedric or the octaedron? Then the visualizers have problem with this. Okay, so we have water molecules. Then we add ions. We can just neutralize the system, looking at the charge of the system and just adding, yes?
See the option. What's different salt selection options? Because in my case,
it's not? Okay.
Yeah, I know how to change concentration from my food, but I get it.
I don't remember. Should it be in the gen ion? I don't remember that. Separation seed neutral, replace group with someone. You're right. You're right. We are missing this one. Yeah. This is for, again, this is something that in Amber you can do with delete. You just modify. Yeah. Yeah. If you can just put this in the Google Doc, that would be fantastic. In the Google Doc that we have, in the shared one, just for us to remember that this is missing. Thank you. Yeah, right. Okay, so we are adding ions again. We can neutralize depending on the charge of the system of the protein that we have, or we can add an ionic concentration if you want. We need 2 steps here. And again, this is specific for GROMACS. We need 2 steps because for GROMACS, adding the ions requires the TPR file, which is the portable binary file that you also need to run the simulation. And for that, you need to run the GROM PP before running the gen ion. So 2 different commands. The first one is generating, in this case, a kind of a dummy TPR file. You put just ions. This shouldn't be here, the number of steps, but the ions is the important part here. So simulation type ions is an MDP that we previously configured that is just adding the ions. And we have different MDPs for GROMACS that are pre-configured. It's talking to the GROMACS people for equilibration in MPT ensemble, equilibration in MPT, unrestrained simulation, different type of, and this should be, if I'm not wrong, in the documentation of the GROM PP building block. You have it here. Simulation type, there is a minimization, MPT, MPT, free, and ions. And if you click, you will see the MDP that we are using in this case. So we run the GROM PP to obtain the TPR, very specific for GROMACS, and then we run the gen ion, which is the one that is adding the ions. In this case, we just want to neutralize. You can see in the properties, 0 concentration. We don't want more ions. But this, for example, you can see in the log file that GROMACS is adding 6. Can you see that? 6 chloride, because it seems that the protein has a +6 charge, right? But if you change that to 005, for example, and this is the interactivity that I was talking to you during the lecture. You can run that again. And then you can see that now it's going to try to add 10 sodium and 16 chloride. So this is just modifying the concentration, and you can tune a bit And this happens with every cell. And then you can inspect again. NGL is going a bit slow here, but I hope that you can see the system. In this case, we have hidden the water molecules for you to see just the ionic atoms that you can see here. So this is a chloride atom, and you see that always doing the same. Need to put that here. So this is the chloride atom. If you hover on top of the atom, NGL is giving you information about which kind of atom name, atom number, and everything. And this is a sodium. You will not see sodiums if you didn't change the concentration. You can do that if you want. And then we start the process of the classical process of minimization and equilibration of the system. I'm going to be quick on that, but as you can imagine, it's the same again and again, 3 different steps. 1 to generate the TPR, very specific for GROMACS again. Generate the TPR, MD run to run the energy minimization or equilibration or unrestrained simulation. And then we added a new one, which is the GROMACS energy. There is just an inspection of the results along the minimization or equilibration process. So I'm going down to the inspection. So you can run in your open on demand Jupyter notebook, you can run all the cells, you can run the minimization, and then you should see something like this, which is plotting exactly how the energy of the system is going down along the minimization process. For the ones familiar with this, you will see that this is exactly the same tutorial that Justin Lemcourt wrote a while ago. We just ported it to the building blocks. This is kind of reaching a plateau. You can extend the minimization if you want. It's still going down a bit, but well, it's quite okay for a protein like this. And then we do the same to equilibrate the system. We decided to, I don't remember if it's 1 or 2 steps. I think there is 2 steps, MVT plus MPT, very MD, for the ones familiar with MD. But it's exactly the same. Creating the, well, in this case, we are creating an index file again. This is for the coupling of, I think, the temperature coupling or something. Yes, to avoid temperature coupling, a new system group will be created. So the information is it's in the documentation. So we need to create a new group with an index file in GROMACS to tell GROMACS this is the group that needs to be coupled with the temperature coupling. So the index, we generate the TPR. The only thing that we are changing here is the type of the simulation. In this case is equilibration with MVT. And here we are defining, do you remember that we generated the restraints for the small molecule? Here we are activating the restraints. We are telling GROMACS, okay, now for this equilibration process, please activate the restraints for this small molecule. For this group of atoms, it doesn't know that it's a small molecule. It just takes this index file that we generated at the beginning and assigns these force constants X, Y, Z that we also generated at the beginning to this particular selection. And this is just telling GROMACS, okay, activate this. Different in the engines, different ways to define exactly the same. We generate the TPR, we run the equilibration, we look at the results of the equilibration. In this case, you see it's just 10 picoseconds. That's why I was telling you before that this is for educational purposes. So if you are trying to set up your own system, you should extend that. You should also extend the minimization step. But in this case, it's even more important. You should extend a lot this. And you should see something like this, oscillating around 300 Kelvin. I think that 300 is the temperature that we put in the MDP. It should oscillate, but you should extend that. So you cannot use this Jupyter notebook as, okay, so this is the workflow that I'm going to use for my production. You should extend these different steps and to let the system equilibrate properly. But it's just extending it, actually. It's just modifying the number of steps here. So you just put 1, 2 more zeros here, and this will be extended. But of course, you will need machine for that. You can do it in your own machine. And also, I guess that with Truva would be okay also, but remember that we have a limit of 2 hours, or at least if you have put a 2, when before deploying the Jupyter Notebook, the limit is 2 hours, so it's gonna be killed after 2 hours. Okay. We check the temperature. Then the second step of equilibration, MPT, we do exactly the same. We just modify this simulation type here. We are now moving from MVT to MPT. I'm not going to explain the ensembles of MD here, but if you are curious, we can talk about this during the day. And then we inspect. I don't know why this is like, like so small, but this is, again, should be oscillating around 0 in one case, 1000 something in the other case. This is pressure and density, but you should extend that if you want to do that in a production system. And then the unrestrained or free MD simulation. Once the system is equilibrated, you can start with an unrestrained. Then I also get always the question here that why do we need an unrestrained simulation here instead of just a production one? So can I take this topology and coordinates that are the output of the equilibration phase and go to the supercomputer and run the production phase? To me, this is a really important process because this is the one important step. Is the one that is going to tell you if your system is really completely equilibrated. Because imagine that you go to a supercomputer, you wait for 2-3 days on the queues before starting the production run, and when the production run starts, it crashes because it's not equilibrated. You have lost like 4 days. So just do this step in your own computers, try to make an unrestrained simulation, see if the system is evolving, is completely equilibrated, and then move to a supercomputer and run the production microseconds MD simulation. And again, this is, as you can see here, just modifying the number of steps. You modify this very short production simulation to a very long, if you want, production. The final part of the workflow is just to demonstrate that there's also analysis, what we call quality control analysis that are integrated here. The first one is the RMS. You all know about the root mean square deviation, how the system is changing a long time during the simulation. And even we just have run, I don't remember the number of here, 50 picoseconds, which is nothing. We still have some frames that we can take a look and see the RMS. And this is what we are doing here. This one here, I hope that you can run and see that. With Plotly, you have 2 different lines. One is the RMSD against the first structure, the one after the equilibration. The second one is the RMSD versus the experimental. So comparing the frames that we obtained with the simulation against the experimental, the one that we have downloaded at the beginning, very beginning of the workflow. And you see how it changes. Remember that in GROMACS, this is nanometers. In the other engines, this is angstroms. In GROMACS, is nanometers. So this is 0.8 angstroms, 1 angstrom, so nothing.
You want shows the other bits? So
We
structure after we obtained from the MD simulation and also with respect to energy, right?
The RMSD versus first, the RMSD versus the first snapshot, so the blue one is the RMSD against the structure that we obtained after the equilibration process. And the red one is against the experimental structure. That's why we are starting from 0 in the production phase. And here we are starting from something that is already different from the one that we obtained from the PDB file, from the PDB database.
It's reasonable to calculate the RMSD with respect to the structure after we obtain the minimization.
You could do that, yes. It will be something in the middle, I guess, yes.
After taking the PDB file from the experiment, we are adding the water molecules.
Yes. Yeah. But that's why we are doing against the equilibration. So here you can compare both. But yes, you can do also that, yes. This is just one example. We have also the radius of gyration, which is telling you the difference in shape, how the shape of the system is changing along the simulation. And in this case, it's changing a bit. The scale is misleading here because it's really small. So it doesn't mean that this big change is changing completely the protein. It's just that this scale is really small. So actually nothing is changing. And hopefully we will be able to see that in the last step, in the last cell of the workflow, where we have this trajectory NGL viewer to see the trajectory. But before seeing the trajectory or visualizing the trajectory, you know, there is a post-processing to remove periodic boundary conditions, again, very MD specific. This is something that it's included in one building block that is called GROMACS Emacs that is using trajectory convert tool in GROMACS with different parameters to image the trajectory, so to remove periodic boundary conditions. And I'm going straight to the last cell. And if you are here and you can do something like this, this is the protein, this is the small molecule that we have prepared. And this is the simulation. I think that we have just 5 frames or something like this, but this is a complete workflow that you can reproduce. At home, you can try to play, you can modify the input PDB, you can take the complex that you want, you can play with the different steps, you can do whatever you want and see if you can reach the final part, which is, okay, so I have the system ready for an MD simulation. So I can now take this information, go to a supercomputer and run a production simulation. But this is the first step. And it's always the same. It seems that just preparing a system, preparing a protein or a protein ligand complex like this to run a simulation, it's nothing, it's just a pipeline, but it can be as complicated as this. And it can be much more complicated if you add protonation states, if you add modeling of backbone atoms, missing backbone atoms, or many other things that I can think about, like histidine protonations or covalently bonded small molecules or ligands or or PTMs. I mean, it can be really, really complicated, as most of you already know. But this is for education purposes. This is the workflow that lets you do that with a simple, let's say, complex. Questions? Have you been able to follow till the end with the notebook? Everything worked fine? Yes?
I couldn't, I ran the course, but the video did not play, exactly.
The video will not play in the end. Yeah, I don't know. Yeah. If you run again the cell, sometimes it happens. Okay. And now you click on this one to see, I don't know how to call it. I click on this one and then play, and then it goes like forever. In loop, exactly. That's the word. Yeah. Okay, if you have questions, there is the document, the Google document. I'm sure that now you are thinking about 1,000 different ideas or comments, suggestions, problems. Please tell us. Everything will be welcome, right? Even if you think that there are many problems associated to that, just tell us. And if you don't have questions, I will go to the third PDF. We are not going to do anything, don't worry. Just 10 minutes or less than that. The extra one, yes. That's kind of homework. For the ones that are interested in exploring what we have, I prepared this PDF. It's again in the GitHub for you with supplementary material, additional Jupyter notebooks, information, instructions about how to use them in the open on demand. which is exactly the same process that you've done today. So git clone of the repo, starting the notebook and start playing with the notebook. These ones I know that are compatible with the environment that I generated in Truba. So you can play with these ones. And I also generated the command line interface for you, the ones that are Python. From the lecture, the ones that I told you that are divided into different files, the Python script and the YAML script. So they are all there. I mean, these 3 examples that you can just copy all the files and you have here. So these are the, I don't know if you can see that, yes. These are the examples. So yeah, if you want to deploy a new notebook, git clone of this specific workflow and then run the notebook. This is for the GROMACS protein MD without the small molecule. This is if we want to do it with Amber, really different MD engine, but exactly the same process, step process. And this is Amber with a small molecule. This is a nice one, which is a protein ligand docking using Autodoc Bina. At the end of the workflow, you can see the difference between the pose that is generating one of the poses. You have like 10 different poses and you need to choose which one do you want to see. And then it is compared against the experimental structure and you can see how much is approaching or is similar to the experimental structure. This is a nice one. And then there's also the free energy, which is a light version of the one that I explained you that we used in HPC machines for the COVID-19 project. This is a light one, of course, with the Jupyter Notebook. Again, educational purposes. We cannot run the whole pipeline, but this is just taking 10 frames and running the thermodynamic integration and giving you the results. This can maybe take more than 2 hours to run, even the educational one. Those are all the workflows, and you have a link again in case you want to explore. And for the command line ones, this is the instructions. You can copy the files that I prepared for you that are placed in this part of the Truba disks. And you can go to the Python folder and run a patch as you did yesterday with GROMACS. You already know that. This is Blurm. You submit a job into the queue, and you can take a look at the launch and see that basically what we are doing is running Python workflows.py, which is our workflow, with the YAML file, which is the input configuration file. Nothing else than that. In the case of GROMACS, this is one of the cases. You will see that there's also the module load of GROMACS in the job, the launch, so that we are using the binary that is compiled in Truba and not the ones that are in Conda. What we said before, that you can use a different binary instead of the one that is in the environment, in the Conda environment. So this is the protein ligand with GROMACS. This is an example of the output. As you can see, this is an EduTeam, so this is running Truba. All the different steps of the protein complex and the setup, the same ones that we have run in the Jupyter Notebook, but here in this case, you just click, submit the job, and then just wait for all the different analyses to be completed. Each of these steps is a folder. If you go inside the folder, you will find all the log files, output files, and everything there. And this is the easy one. This is the one for Amber, exactly the same. And this is the free energy. And here you have the hierarchy of output folders for this. You remember from the lecture, I tried to explain that very quickly to you, but you have the 2 different equilibrium and these simulations, and then we have all the forward and reverse thermodynamic integration. So if you see here, the output of this educational Python script, in this case, workflow, you have a state A and state B folders that corresponds to this and this. And then we have a step 11, it's the last one, which is analyzing the results, which is the one that is producing the histogram and getting the intersection about the 2 populations. If you go into state A, you have all the different frames. So frame A, like this, forward, frame 0, frame 1, frame 2, until 50, all the thermodynamic integration forward. If you go to state B, you have all the reverse ones. And if you go to the step 11, you have a PNG, which is exactly this plot that is telling you this is the delta G. Again, this is 50 frames. If you want to do that properly, we were using 1,000 and we were using many nodes in a supercomputer. But the workflow is quite similar, I can tell you, as this one, the one that we used in the supercomputer. And with this, I think that it's all from my side. Again, remember that we have the Slack channel, we have the Google Docs, many ways to contact us, to tell us what you think about all of this. And I can take questions also now or after lunch.
I think during the hands-on sessions, questions are asked along the way. But in case there are any burning outstanding questions, now's the time.
I have a question.
Go ahead.
So I understand this approach on demand, we do from the environment, we do jobs, and there is an advantage of compatibility. But I ask if, with respect to doing old school from interface going into the supercomputer, transferring files in between computer and interface, and visualization, the time spent on that, the personal time, the working time, in real life time, not computational. If you compare the real life time spent for the same job with this approach versus an old school approach, how can you compare it? Lower, higher? A person's spent time.
I think it's lower time.
Oh.
Let me tell you, yes. Because you have two options, right? You can run everything without visualizing and just thinking that everything will be right and just running this in a supercomputer. You don't know anything about the system. You just believe that the system is correct. Okay, in this case, this is lower time. But in most of the cases, at least in my experience, we are not doing that. We are using VMD. We are trying to visualize what is happening here, where are the key residues, everything. In this case, we have everything in one single graphical user interface. You don't need to jump between one VMD and then the terminal and then the file system. So it's lower time, according to me. Once you have everything, of course, you need to be familiar with all of this before. You need to learn about the tools, the methods, and everything, of course. But you also need to learn about GROMACS before starting GROMACS simulation. So I see your point. I think it's not so much complicated and it's not taking so much time if you start using this kind of tools. Like my opinion.
Often with the initial investment, in my experience, if you're a regular user of such things, in the long run, it will be. But if you're just one of an experimentalist and then you want to try out something more, of course it won't pay off. But if you're like competition, or maybe working with, even experimentalists or regular users, then it definitely pays off to invest the initial time. And also the checkpoints, you also benefit from the knowledge created, accumulated by the people who invested at the time. What points should you look at? What are the things you pay attention to? That's also built into the system, so you also have additional wisdom that comes along.
Yeah. And there's also the point about reproducibility. So start thinking about journals asking you about reproducibility. And if you have something like this, reproduce these kind of things, it's just, this is the GitHub repo. But if you did that one day with one computer, the other day with another one, and then I transfer files here and down, up and down, this is much more complicated to prove that this is all the steps that you follow.
Any other questions? Or online? No online questions.
Okay.
All right.
Thank you.